For hundreds of millions of years after the Big Bang, the universe was completely dark. No stars, no galaxies, no planets. Only endless clouds of hydrogen and helium drifting through space. Just this cold, dark expanse, basically frozen in time, waiting for a massive transformation. Then, gravity changed everything. Welcome to This Explainer. Today, we're going to witness one of the absolute greatest moments in cosmic history. How did the very first stars form, and why did they change the universe forever? Section 1. The Endless Dark. So picture these massive, freezing clouds of hydrogen and helium. They were the silent, lightless nurseries of the early cosmos. According to NASA, these molecular clouds range anywhere from 1,000 to 10 million times the mass of our own sun. And get this, they span hundreds of light years across. For millions of years, they just hung there, freezing, immense, and completely dark. Section 2. Gravity changes everything. Okay, so how do we get from a freezing, pitch-black cloud to a violently burning star? Well, because these molecular clouds are incredibly cold, the gas inside them starts to clump together, creating these high-density pockets. As the clumps collect more and more matter, their gravitational pull gets stronger and stronger. Eventually, gravity just forces these clumps to collapse inward on themselves. And as all that material violently rushes in, intense friction causes it to heat up dramatically. Right there in the heart of that collapsing, swirling vortex, a protostar, a baby star, is born. Section 3. The Spark of Fusion. Now, the protostar is glowing hot simply from the friction of that initial collapse, right? But it needs a monumental atomic shift to truly awaken. After millions of years, the immense pressure and temperature in the core becomes so extreme that they literally squeeze the nuclei of hydrogen atoms together to form helium. When this happens, an absolutely massive amount of energy is released. That is nuclear fusion, and it's the exact moment the universe lit up. The very first starlight and heat finally pierced right through those cosmic dark ages. It's honestly like the ultimate cosmic wrestling match. On one side, you've got the crushing inward pull of gravity, which is constantly trying to collapse the star under its own tremendous weight. But on the other side, you've got the explosive outward push of nuclear fusion. Once these two opposing forces perfectly balance each other out, the star is officially stabilized. Section 4. The Long, Stable Burn. Once that delicate, beautiful balance has struck, the star enters the longest and most stable phase of its life. Astronomers call this a main sequence star. Basically, as long as it's stably undergoing that nuclear fusion of hydrogen into helium, it's not going to collapse. To put that into perspective, our own sun is currently roughly midway through this main sequence stage, just quietly burning its fuel and providing the light and heat that sustains life right here on Earth. Now, what's truly counterintuitive here is how a star's mass actually dictates its ultimate destiny. You'd think bigger means it lasts longer, but it's the exact opposite. The most massive stars actually have the shortest lives. Because gravity is pulling inward so intensely on a massive star, it has to burn through its fuel at a furious rate just to stay balanced. That means it might live for only a few million years. Meanwhile, lower mass stars, they just sip their fuel. Some of these smaller stars will shine for trillions of years, which is vastly longer than the universe has even existed so far. So, this mechanical process of gravity and fusion scaled up across the entire dark cosmos. Molecular cloud after molecular cloud ignited. These stellar nurseries churned out millions of newborn stars, eventually giving us an estimated 1 septillion stars in the universe. Yep, that is a 1 followed by 24 zeros. It's almost impossible to wrap your head around, but the dark ages were truly over. Section 5. Death and Cosmic Rebirth. But as we know, nothing in the physical universe lasts forever. Eventually, that vital hydrogen fuel begins to run out. And when it does, the outward pressure from fusion drops. Gravity, which has just been waiting patiently for millions or billions of years, instantly starts winning that wrestling match. It forces the core to violently collapse inward. This huge squeezing effect causes the core temperature to spike dramatically, making the star's outer atmosphere puff up and expand. Deep inside, just trying to stave off total collapse, the desperate core begins fusing heavier and heavier elements. The final act of a star's life is, once again, totally dictated by its mass. A low-mass star, like our sun, will puff up into a giant, peacefully eject its outer atmosphere as a beautiful cloud called a planetary nebula, and just leave behind a glowing Earth-sized cinder known as a white dwarf. But a high-mass star, it goes out in a terrifying blaze of glory. It fuses heavier and heavier elements right up to solid iron. But here's the catch. Fusing iron doesn't create energy, it absorbs it. Without that outward pressure, the massive core collapses in a fraction of a second, rebounding outward in a cataclysmic explosion. A supernova. These supernovae are absolutely among the most violent events in the cosmos. And when the dust finally settles, they leave behind the most extreme objects known to physics. If the core survives the explosion, it becomes an ultra-dense neutron star. But if the original star was massive enough, the core's gravity is so immense that literally nothing can stop it from collapsing into a single, infinitely dense point. A black hole, where not even light can escape. But here's the amazing part. These violent stellar deaths are not tragedies. They are a cosmic rebirth. As NASA notes, the material cast out by supernovae will actually enrich future molecular clouds and become incorporated into the next generation of stars. In their dying moments, these massive stars forged heavy, complex elements like carbon, oxygen, iron, and silicon, and scattered them right back into the dark molecular clouds. To wrap up this explainer, I really want you to consider this profound reality. The very first stars to light up the dark universe completely destroy themselves. But in doing so, they seeded the empty cosmos with the heavy elements absolutely necessary for rocky planets to form and eventually for biology to exist. We are quite literally made of the ashes of the first stars. So, it begs the question, as our universe slowly ages toward an eventual return to eternal darkness, what new wonders and what new possibilities will our current generation of stars leave behind in the dark? Definitely something to think about next time you look up at the night sky.